and say my C to D is here. So I'm talking about this rectangle. So it's a rectangular region. And I want to know what is the probability that x stays between A to B and y is in this interval C to D. Okay? So you can compute this by simply computing the integral of the given joint PDF with respect to x first with respect to y. So the x is in the interval A to B and y is in the interval, what do you call, C to D. So just compute this double integral and then you can have these probabilities for the continuous time random variables actually. And I mean, I hope that you also know that how to compute such probabilities. So first you can do is that, okay, compute this integral with respect to x, and whatever the outcomes comes, you compute it as the integral with respect to what you call y actually. So that's how you're going to compute the probabilities. So let's do one example. Let's do one example. By the way, one of the things that you can ask, what would be the marginal distribution function of x in case of continuous time random variable, and what would be the marginal distribution function for y? So in other words, if you want to, for example, compute say fx of x actually, and you have been given a joint PDF of x and y, so how you can do it, it's really analog to what you have done in what do you call in the discrete time case. So what you can do is that, so what does this mean is that what is the probability that x is x? So if I have, what is the probability that x is y, x is x, so what can I say about the probabilities, what can I say about y? So you're going to say that y can be anything actually. So it can be something between, so it can be anything between minus infinity to infinity, because y is a random variable that takes the values in R actually. Okay? So what would be the explicit way to write this? So what you need to do, so this is like a single integral actually. So this is like, okay, so this is like you have so what it would be that, okay, you compute the only single integral thing. So see, like this is fixed actually, x equal to x is fixed. So only y is variating. So if you want to compute such probabilities, what you need to do, so you can take your fxy, evaluate it at x, where x is a fixed number. Okay? I mean, if you wish, you can put a number, say a, so that you shouldn't get an illusion that, okay, maybe you are talking about the fixed, the small x being, a variable. So I'm talking about a fixed x actually. So what you need to do, so just take your fxy, compute it at a, and then integrate with respect to y. Okay, from minus infinity to plus infinity, and you're gonna get what you call the marginal distribution function of x actually. And similarly, you can also have a marginal distribution function for y by integrating the joint PDF with respect to x from minus infinity to infinity. So I hope all these things are making a little bit sense to you. So let's do some examples. And let's compute some of the probabilities. So here is the example 1C from the book. So it says that imagine you have been given a joint PDF f of x, y of random variables x and y, and the joint PDF goes like this actually. So the 2e to the minus x times e to the minus 2y, okay, where x is between 0 to infinity and y where x is between 0 to infinity and y is also between 0 to infinity. So you are talking about the first quadrant actually. Okay? So you are talking about the first quadrant where x and y both are positive. And it's equal to 0 otherwise. Otherwise actually. You can also write it as single function, that this is going to be e to the x plus what is equal to y. Okay? E to the x plus 2y. So in other words, it's a, so what is the definition of this? So the definition of this is that, okay, in the first quadrant when x and y both are positive, f of x, y takes these values, and while in all other places it's equal to 0, 0, 0. You can ask a first question, obviously, is f a PDF? Is f of xy a PDF actually? Is it a PDF joint density a PDF function actually? So the first of all, the first thing should be that, okay, is f of xy between 0 and 1? The answer is yes actually. Why? Because think about it. So if so the exponential is never 0. Exponential e to the x is never 0, no matter what x you choose, and it's always a positive number. Okay. So it is. So this guy e to the minus x plus 2y is for sure greater than 0. Why this is less than or equal to 1? Because if you take two positive powers and make it, what do you call, the negative exponent of the exponential, so this is like having 1 over e to the x actually. So if you have 1 over e to the x when x is a positive power, then this is a number less than 1 actually. Because the numerator is, you know, a numerator is smaller and the denominator is big actually. Okay, so this must be the case. So indeed, if you have, for example, 2 here as well. Okay, so the exponential e to the minus x is an obvious fact that it always lies between what we call 0 to 1 for any values of x actually. So this must be between 0 to 1. Okay. So what is the second property that it must satisfy? So it should satisfy this identity that if you integrate it from minus infinity to infinity, okay, so it should give you what do you call 1. Okay. So let's compute the integral from minus infinity to infinity of f of x, y, which is e to the minus x plus 2y dx and dy. Okay. Now this function has been defined when x is between 0 to infinity and x is between 0 to y is between 0 to infinity. So this integral, okay, in all other places is going to be equal to 0. I must write f of xy. F of xy. But this will only exist. It will only exist when x is between 0 to infinity and y is also between 0 to infinity. Otherwise, at all other places f of xy is 0, so the integral would also be 0. It's going to be e to the minus x plus 2y, and we have now how to compute this integral. Okay, so it's not a big deal. So if you want to, for example, integrate with respect to x, so this function with respect to y is like a constant. You can pull it out of integral if you wish, so e to the minus 2, there should be 2 as well. Okay, there should be 2 as well. The first, so you can, take this, for example, 2 outside completely, and e to the minus 2y outside of the first integral, and keep the e to the minus x dx inside and compute the integral actually. So I'm assuming actually that you know a little bit of you have a, what do you call, a good understanding of how to compute the double integrals actually. Okay, that's an important thing. Now, so since this integral y is like a constant, so you can pull out that term, and what is remaining is this. And now 0 to infinity e to the minus 2y is going to be e to the minus x and minus, and you have 0 to infinity dy. So it's going to be e to the negative infinity, which is 0, and e to the minus 0, which is going to be 1 actually. So it's going to be 0 and minus minus plus 1. So you substitute minus infinity, not substitute, but as x goes to minus infinity, e to the minus x will go to 0, and as you substitute the 0, you're going to get e to the 0, and minus minus will become what you call plus actually, so this is going to be 1. So 2 times of 0 to infinity e to the minus 2y times 1 dy. And then you can integrate it also. So you're going to get e to the minus 2y and everything divided by minus 2, and substitute the value infinity. So as y goes to infinity, this will be 0. Okay, so 2 by 2 is going to be minus 1, or maybe only minus. And e to the minus infinity, or as y goes to minus infinity, is going to be 0 minus e to the minus 0, so it's going to be e to the 0, so it's going to be equal to what is called 1. So you can see that it really satisfies the properties of being a continuous time PDF. So this is an example of continuous time PDF. Now let's compute some events actually. So imagine you have a continuous time PDF which is defined over the entire domain, okay, so it's defined over the entire R2, okay, because x is defined over R, y is defined over R, so f of x, y should be defined over the entire R2, okay. It has non-zero values only in the first quadrant, but in all other quadrants it has value 0. So now let's take some other subsets of R2, and using the PDF that is defined over entire R2, we will try to compute the probabilities of those subsets. For example, so here's an interesting example. What is the probability that x is bigger than 1 and y is less than 1 actually? Okay, so this is what that I would like to compute. Now, by the way, we need to think about that. What is the meaning of x being bigger than 1? So when I'm saying that x is bigger than 1, what does this mean? Is that x is between 1 to infinity, because like this is this take a non-zero value between 0 to infinity. So if x is bigger than 1, okay, so if you make a real line and you say that okay, I have 1 and x is bigger than 1, so you are talking about this region actually that goes from 1 to up to the infinity. And what is the meaning of y less than 1? So you're going to say that okay, y is less than 1 but bigger than what you call minus infinity. So this is the case. And then I can write this as the integral, so it's going to be a double integral. I can directly write, keeping in view the limits of the outputs. Okay. So this is going to be 1 to infinity, and you can say that this is minus infinity to 1 f of x y and dx dy. But we know that Okay, so I mean, if you want to, it's always good to have a look at that what kind of a region you are talking about. So what is x equal to 1? So maybe x equal to 1 is this. Okay? This is x equal to 1. And what is y equal to 1? So the y equal to 1 is maybe this actually. Okay? Now what is the region that represents x bigger than 1 actually? So this is the entire region that represents x bigger than 1. And what is the region that represents y less than 1 actually? So this is the region that represents y less than 1. So where are those where you have, what is the intersection of the both? So the intersection of the both is this region actually. Okay, this entire region, while this is x-axis. Okay. I know that function does not take values here actually. So it's 0 here, it's 0 here, it's 0 here. Okay. This will not be counted. Okay, so or this region will not be counted because this is not y less than 1, so only this part will be counted. So you have to integrate in this region. Now what are the limits on this region actually? Just think about it. Okay. So you're going to say that okay, y starts from 0 and goes up to 1. If this is y equal to 1, 0 to 1. And x goes from 1 and goes on forever actually. So it's 1 to infinity. Okay? And the value of the function in this region, because this region is a part of the first quadrant, is going to be this actually, which is e to the minus x plus 2y and dx dy. Okay? So using the same trick, you can, what do you call, compute, as you computed the integral here. I'm not doing the computation again, so you can get something like this. So that goes like 1 minus e to the negative 2 divided by e. Okay, so this is what is going to be the region. There is another interesting probability that you can compute. For example, okay, so the continuous time case is a really interesting one. You can also see all this stuff as the application of calculus to the probability theory actually. So you can see that how the double integrals and the single integrals and the double sums and higher sums, they are representing the different kind of probabilities. What if I try to ask, say, from you, what is the probability that when x is less than 1? Well, that's an interesting thing actually. That's an interesting region. So I want to compute this for the given PDF. So always when you have such kind of probabilities in a continuous time case, try to plot your region. Try to compute all points of intersection of these two regions actually. Okay? And then see that what is the value of the joint PDF in that region, and then compute that integral actually. Okay? So what is x less than y? In other words, I want to see this region. So to see this region, what I can do, I can plot x equal to y. So what would be x equal to y? So the x equal to y could be this line actually, so the diagonal line. Huh? This is x equal to y. Now which region could be the, what do you call, x less than y region actually? So y is big, so if I take for example a point here x is 3, for example, so this is say for example a point 3, 0. So you are talking about a region where x is big and y is small. How about if I pick a point here? So you're going to say that, okay, my x is, for example, 1 and y is 3. Something, or maybe x is 0 and y is 3. So, and you take this region point actually, so you're going to say that, okay, y is bigger but x is smaller actually. So what is x bigger than y? Okay, x bigger than y. So it talks about all this region. So this is all region which is x bigger than y. Okay, so this is all region which is x bigger than y. Now, keeping in view the definition of, by the way, this line is not included, x equal to y line is not included. So, keeping in view the definition of the PDF, the joint PDF only exists in the first quadrant actually. So, it's 0 here, it's 0 here. So, the only thing, in other words, the double integral that you have to compute in this region. Okay? So this bit of triangular region actually, we need to compute the region here. So I need to integrate my f of xy. So if I want to compute, for example, what is the probability that x is less than y, I need to compute the double integral of f of xy dx dy in this region R actually. So this region R. Okay. Question is, what are the limits on x and what are the limits on y? So in order to take the limits or write the limits on x, you have to think that, okay, in this region how x is variating. So it starts from where and it always ends where actually. So the x starts from always from here where x is 0 and ends where x is y. So 0 to y, 0 to y, 0 to y, and so on and so forth. So the limits on x are 0 to 1. And how about y? So y goes from 1 to infinity. Okay, so it can take any value. So it's, y equal to 1 to infinity. Okay, and then we know that f of xy in this part is 2 times of e to the minus x plus 2y. By the way, I must write a 2 here. Okay, and then compute this integral actually. But in this integral, the limits are a bit variable actually. Okay, so that's an important thing that you need to keep in view. So first integrate with respect to x, and then substitute the limits, and then integrate with respect to y, and you're going to get something like this. So I'm just directly writing the result of it and leaving the calculations for you, so it's going to be 1/3. Okay. So it's an example 1b, okay, from the book, but I'm going to present, kind of a different version than what it says in the book actually. So, kind of a more practical version. So imagine you have a board, okay, a dartboard, okay, so on which I can throw the dart, and the dart can hit any point in the given, what do you call, circle. Imagine that this board has a radius, what do you call, r. Okay, so the radius of the board or the circle is r. Now I'm hitting the dart. Okay, the dart. So there are two possibilities. Dart cannot hit the circle, board of the circle. It can. So if I'm okay, if I'm bad at throwing the darts, so my dart can miss the circular board. Okay, or it can hit the circular board. So let's assume that I am at least that much expert that when I am throwing a dart, it is going to hit the board actually. So where it is going to hit? So I know that where it is going to hit actually. So it can hit here, it can hit here, it can hit here, it can hit here, it can hit here. Okay, so it can hit at any point. Let's imagine that this board is in 2 dimension, okay, and the coordinates of the points where the dartboard can hit, on this board is xy actually. So I don't know that what is this xy. So the point xy could be this, point xy could be this, point xy could be this, and so on and so forth. So all points of the region have an equal chance of of being hit by the dart actually. Okay. So I have a dartboard. I'm throwing a dart, and the dart hits at any random point within that region. What do you call R actually? Okay. So the question: what should be the PDF? The PDF of this, so the f of xy, where x is the value taken by x and y is the value taken by y, is going to be some constant, for example, which I don't know, since all points have equal chance actually. So this is an important thing. By the way, you can guess it actually. It's not difficult to guess that what should be this point. I mean, if you want to compute this probability. So in other words, this should be, in principle, 1 divided by the area of the square actually, which is pi r square. Okay. So this must be the probability when x and y hits the point on the region R. But here I want to determine this point through another, what do you call, source. So let's call this that this probability is equal to C, which I don't know yet actually that what is that probability. I'm going to determine it soon. So f of xy is C if the dart hits the board xy. Okay, if the dart hits the board at any point here, and when the dart hits the board, then the distance between the point where it hits and the center is going to be what? It's going to be x square plus y square. Okay, so I can also imagine that this is really the origin actually. Okay, I can imagine that this is the origin. Maybe I redraw the picture. And I say that the center of the dartboard is really origin, okay, and the radius is r, and this is a point where it hits the dart actually. So dart can hit within the board or outside board actually. So if the dart hits within the board, then the distance between the point and origin must be less than or equal to what